Sometimes a function is not expressed in terms of x explicitly, such as f of x equals to x squared. Instead, the function is defined implicitly by an equation that it satisfies. For example, the upper half of a circle can be defined by the equation x squared plus y squared equals to 1. Y is assumed to be a function of x, so that y equals to f of x. Then f satisfies the equation x squared plus f of x squared equals to 1. We can still find the derivative of f by what's called implicit differentiation. In implicit differentiation, we take the derivative of each side of the equation and solve for dy dx. Let's take a look at an example. Find dy dx if x squared plus y squared equals to 1. Take a look at this equation right here. We want to differentiate both sides. So the derivative of x squared is 2x. And here, notice that y is a function of x. So this is really f of x to the power 2. And we have to apply the chain rule. So this will be 2y times the derivative of the stuff inside the power of 2 here. So that would be the derivative of y. And derivative of 1 is 0. Okay, now we want to solve for dy dx. So subtract 2x from both sides. Then divide by 2y. Okay, so the 2's cancel out. And we just end up with negative x over y. Note that dy dx is a function of x and y. It's not just a function of x. The graph of x squared plus y squared equals to 1 is a circle of radius 1. Okay, here's the graph of the circle of radius 1. If we solve x squared plus y squared equals to 1 for y, we get y equals to plus or minus square root of 1 minus x squared. Y equals to square root of 1 minus x squared gives the upper semicircle, and y equals to negative square root of 1 minus x squared gives the lower semicircle. We'll focus on the upper semicircle as our function. So here's the upper semicircle, and y equals to f of x. Let's look at a point here, square root of 2 over 2, comma, square root of 2 over 2. Let's look at the derivative at the point square root of 2 over 2, comma, square root of 2 over 2. Okay, the derivative is given by negative x over y and we want to find the derivative at that point. Square root of 2 over 2, square root of 2 over 2. If we plug in this value for x and this value for y, we get this. Okay, and this cancels out, so we get minus 1. So the derivative of y with respect to x is minus 1 at this point. Okay, here's the same graph with the tangent line at that point. Square root of 2 over 2, square root of 2 over 2. The slope of the tangent line at that point is negative 1. Okay. Now the slope at the point 0, 1, which is here, 0, 1. Okay, the slope at that point should be 0. Let's verify this by finding the derivative. Okay, here I have the graph with the tangent line at 0, 1. Okay, let's find dy dx. Remember, that's negative x over y, and we want to evaluate at 0, 1. Okay, plug in 0 for x, plug in 1 for y. So we get 0. Okay, the derivative is 0 at that point, which verifies the fact that the slope of the tangent line is 0 at that point.